All right, let's talk about the concept of electric field. Now, electric forces, when I have two charges, the forces they experience due to each other, in case of like charges, these electric forces, of course, will repel. These are considered long-range forces, meaning these charges do not have to physically be in contact with each other for the forces to exist. For example, my laptop is sitting on my table at the moment. There is a normal force from the table because of the fact that the laptop is sitting on it. If I lifted my laptop and it was no longer in contact with the table, then that force, that normal force specifically from the table, would no longer exist. So most forces we've dealt with, like in 2210, our first semester of physics, most of them were contact forces. But of course, we did deal a lot with gravity, which is a long-range force. You may have heard it referred to sometimes as well as action at a distance. I've heard that terminology before, where this charge 2 over here is experiencing the force even though it's some distance r away from charge 1. Whenever we have long-range forces, we can talk about them in terms of field. In this case, electric field, meaning how, for example, charge 1 is affecting the region of space around it, such that, in turn, charge 2 will experience a force. So it's kind of an abstract thought, but it was a helpful way to think through these long-range forces. And these concept of fields were explained, or even just invented of sorts, by Michael Faraday. He was playing with iron filings. I'm going to show you just a little video where the person has some magnets, and then they put a piece of really thick, maybe poster board type material above it, and then they shake little pieces of iron on top. So just for a second here.
Over the top here, and we finally got a piece of paper that's not glossy, so this ought to be easier to see. All right, there's our magnetic field lines. As I tap it,
Okay, so as he taps it, that iron, these little shavings of iron will line up. Now, in this picture, let's see if I can write so that you can see it. Oh, nope, apparently I decided to zoom in. Sorry about that. Okay, we can still see this though. So Michael Faraday this is something any of us could play with. Get some magnets, get some little pieces of iron. And even though none of these pieces of iron are physically in contact with the magnets, they are lining up. See, notice how we see these arcs. They're lining up along these lines that point between the two ends of the magnet. So where these are concentrated at those ends are the ends of the magnets underneath the paper. So each of these little pieces of iron are being affected somehow by the magnet. And so Michael Faraday, in terms of conceptualizing this, talks about a magnetic field at every location around these ends of the magnet. And it's this field that we can think of as being the acting agent exerting the force on these little pieces of iron. We're going to talk about magnetic field later. Right now, we're going to talk electric field. So I have one other little video clip I would like to show you. Let me erase my lines first. Okay. So to visualize electric fields, you may have seen a Van de Graaff generator before. I'm going to show you just a clip, and then I'll also include this link so you can watch the whole video if you would like. A Van de Graaff generator, there is a rubber belt inside this vertical tube, and it just goes around and around and around, and it deposits charges on this metal sphere. Well, metal is a good conductor, so those excess charges go to the outside surface of the sphere. This presenter is talking about how your hair will stand up, but that his hair is too heavy for it to work very well. Which I've seen this. We have a Van de Graaff generator at school, and we've tried it on many different people, and it does not work equally well for everybody. It does work very well for me because I have very fine hair, but I am not able to take a video of it today to show you. So I'm going to show you this one.
My hair is actually too heavy to use, so I got this here wing to help us.
So what we're seeing with this is there's these electric forces occurring. The charges are trying to get as far away as possible. So now they don't have to stop at the edge of this sphere. They can actually physically travel to some extent down the hair fibers, which means all these little strands of hair get charged, and then they are repelling each other, which is why this hair can stand up. If I remember when I'm back on campus next week, I'll do this with my hair just because it's always entertaining to see it on a real person. So electric field is what we're talking about here. It's a way to describe, for example, that sphere on the Van de Graaff generator. I can't recall if a Van de Graaff generator ends up positively charged or negatively charged. I'll just go ahead and work with positive. The electric field would look somewhat along the lines of what we're seeing that those hair fibers do. It points outwards, away from the sphere. It does point out three-dimensionally, which I'm not very good at drawing three-dimensionally. So just know that it would be coming out of the screen at us. Regardless of which side of the sphere we stood on, we would see the hair moving outwards. This electric field, we think of as the acting agent on a charge that would experience or feel a force if it was placed in this field. So if I had a little positive charge, your book calls this a probe charge. I am used to calling it a test charge. Ultimately, we just mean the charge that feels the force, experiences the force because of where it is located near this other charge. These are both positively charged. the probe charge is always positive, this little charge would feel a force that points directly away from this sphere that I've drawn. If I place this little charge closer to the sphere, it would feel or experience a larger electric force, which in terms of Coulomb's law makes sense, I hope. Two positive charges, the force depends upon how much charge there is and how far apart the charges are located. So I can take a little probe charge or test charge and I could put it anywhere in this field, and I want the field to represent how or what type of force this probe charge or test charge would experience. The electric field was described, so we're going to use a capital E to represent electric field. It is a vector. It has a direction associated with it. The electric field was defined and described as the force this test charge feels divided by that charge, the charge on the test charge. So our author is calling it a probe charge because it's almost as if this is an electric field probe. We know there's an electric field at a location if we place a charge there and that charge experiences an electric force. Okay? And so the electric field describes just how this charge that's creating the electric field, how it's influencing the region of space around it. Which in turn, to probe for an electric field, we would have to place a test charge there to see if it has an electric force. So with the definition of a probe charge being positive, we know any positive charge placed nearby another positive charge will experience a force that points away, the electric force pointing away. We find that electric field lines always point away from positive charges creating them, creating the electric field specifically. So we do need to distinguish between our probe charge, the one feeling the force, and our charge that is creating this electric field. So ultimately what it boils down to is the charge that creates the electric field is the one that's going to cause other charges to feel a force. It's the acting agent. The test charge or probe charge is the one that is actually experiencing or feeling the force because it is nearby this charge that's creating the electric field. Now, fundamentally, yes, every single charge would create its own electric field. That is totally true. So in any one given situation, we have to decide which charge is creating the field versus which charge would be feeling the force. All right, so electric field lines, E always points away from positive Q. For the sake of distinguishing between the charge creating the electric field and the one that would feel the force, I'm going to use a capital Q to represent the charge creating the field, and a lowercase q to represent our probe charge or test charge that is feeling the force. Now, I know they don't technically have feelings, but experiencing the force. Feeling is just an easy way to explain it. Okay, so one general rule, electric field lines always point away from positive charges. So if I have a positive point charge, a positive capital Q, its electric field will point radially away from it, three-dimensionally, all directions. So three-dimensional, all directions. And we know that because we've defined this probe or test charge based off of it being positive. And we know a positive charge would be repelled by this positive charge. Well, the charge creating the electric field does not have to be positive. It could be negative. We could have a negative capital Q, so a negative point charge creating this electric field as well. But if I were to place a probe charge here, I know it would be attracted. The force would be towards this charge. That means the influence that this charge has on this region of space around it is these inward pointing electric field lines. So electric field always points towards negative charges that are creating this field. This is three-dimensional as well, meaning that you're coming in from every direction towards a sphere. If we have a combination of charges, let's say we had a positive Q and a negative Q, and we want to account for both of them contributing to the electric field and see what an overall electric field would look like. The overall electric field in any region of space around charges is simply the sum of the electric fields due to however many charges we have. Here I've drawn two, so we would have an E1 and an E2. I'm going to call our positive charge 1 and our negative charge 2. Okay. When we want to talk about the electric field at some point in space, so this point I've drawn does not represent a charge. It just represents a point in space. I know that this positive charge is creating electric field lines that point away from it. That would be an E1. If we think back to this picture, I know a probe charge placed closer is going to experience a bigger force compared to a point charge or test charge farther away. That means the electric field is stronger. since we've defined the electric field as the force divided by this test charge, if the force is bigger on this same probe charge, then the electric field is bigger as well. And actually, interestingly enough, if we think about just that charge at that distance versus a charge further away, in a picture, the field lines being closer together means a stronger electric field. If you look in a region and the electric field lines that are representing the electric field, if they're farther apart, that represents a weaker electric field. That would be true around this negative charge as well. These are closer. The closer electric field lines represents a stronger field. Doesn't represent the direction. We have to represent the direction with these arrows, but it just means it's strong. The further apart, farther, I don't know which is appropriate here. I'm not an English guru, sorry. Means it's a weaker field. Just means the force on a charge won't be as big out there as it would be in here. Now, the reason I mention that is this distance that I've drawn this point in space, R1, is less than the distance from this negative charge, R2. The farther away I get from a point charge, the weaker the force on a test charge would be. So if I've drawn E1 with this length, when I draw an E2, the electric field due to charge 2, I need to draw a shorter vector. Because this charge 2 is negative, the electric field would point directly towards it. So those are some of those general rules. Electric field lines point away from positive charges and towards negative charges. At this specific point in space, both charge 1 and 2 are creating their own electric fields. So the overall electric field at that point in space would be the addition of those two vectors. So vector addition, the total electric field right here, E total or overall, would have a rightward component and an upward component. When we draw that vector, we just mean at this exact point in space, that is the electric field. That's the strength and direction. And we could find the force on an object that, or a charged particle that was at that location. What if, though, we consider a point in space that's equal distance? So R2 and R1 are exactly the same to get to this point in space. Well, charge 1, because it is positive, is still creating an electric field that points directly away from it. Charge 2 is also creating an electric field that points directly towards it. But if we're talking the same distance away and positive Q and negative Q have the same magnitude of charge, those y components are going to cancel. If we add these vectors together, we will get an overall or total electric field vector at that location that points directly to the right. So ultimately, to see this come together, we would have to think about a whole bunch of points in space. What does the electric field look like at all these points? Which, of course, we're not going to take the time to do. What it ends up looking like if we were to just draw lines that represent how these total electric field vectors point, it would look like this. We would have some lines that point directly from left to right, from positive Q to negative Q. We would have some that go up and back down. So remember this E total up here, because we were closer to the positive Q, that had a bigger E, which is why we got a field more so pointing away from positive Q than negative Q. If we were to get closer to negative Q, we start getting these downward lines. So ultimately, we get a setup where we would have electric field lines coming out from positive Q, going in to negative Q, and these lines represent the general look of the electric field. The actual value and actual vector at any point is tangent to these lines. If I wanted E right here, I would draw my E tangent. And it is still true that the closer they are together, the stronger the field is. The farther apart, the weaker. Okay. In the case of having equal magnitude charges, this is called an electric dipole. So positive Q and negative Q have the same magnitude of charge. We have what's called an electric dipole moment. To talk about how a dipole would respond in another electric field, which we'll talk about this more later, but I do want to give you this equation before I forget. So electric dipole moment, our author uses a lowercase p to represent it. It is determined by the magnitude of the charge. And they have to be the same. So the magnitude of either charge. S is the distance between these two, just straight line distance. The direction is opposite the electric field, which we'll explain why later. So if I draw P, this electric dipole moment, on here, then it points from negative to positive. So direction is negative to positive. All right, so the electric field points away from positive towards negative. This electric dipole is just a specific case where we have a positive and negative charge with the same magnitude. I'll talk about the equation in just a sec, but I want to show you, just from a simulation, kind of an easier way to see this than me trying to draw. So we have here a positive charge. I can put it anywhere I want. Notice these arrows move around as I move the charge. They are representing the direction of the electric field at the little black dot that is within the arrow. So almost as if they're compass needles. The way that this simulation is representing the strength of the field is the brightness or the shading of the arrows. So we can see as we look farther from the charge, we see the arrows get dimmer and dimmer and dimmer. And that's because the electric field will get dimmer and dimmer as we move away from a charge. Okay, so arrows, think of that little dot right there, the arrows representing the direction at that dot specifically. I can pull out other charges. 2 positive charges. Notice in this region in between the two, we get a really faint arrow. If these charges are identical, there would have to be a total electric field of 0 in the middle, because both of them would be creating their own electric fields that point away from them, and that would be the same strength, so those vectors would cancel. We can change the amount of charge, the strength. We can put, let's actually reset this for just a sec so I can show you what I was representing with that electric dipole. We see that general form of the electric field lines pointing from positive to negative. Now, this particular simulation does not separate the distance of the arrows to show whether the field is stronger or weaker. It's the brightness of the arrows. And even then, it's not perfect. But it gives us an idea. So we can put all sorts of charges out here and see how the electric field changes. As far as what we might calculate is we might want to find the total electric field due to, say, 4 charges. And so to do that, if I come back, the total electric field due to multiple charges is simply the electric field of the individual charges calculated at the point of interest, all of these added together. And technically we can add as many electric fields as we need to. So as far as electric field goes so far, we have 2 equations. Well, I've given you one of the equations. I'll give you the second as well. So the electric field was defined as the force that probe charge or test charge would experience divided by its charge. And ultimately, we can find the force, electric force specifically, on any point charge that's placed in an electric field with this same equation. If we know the electric field at a point, we know the point charge we put there, we can calculate for the force on it. The other equation we have is for the electric field of a point charge specifically. I guess maybe electric field created or due to, created by, or due to a point charge. When you look at the test notes, these equations are actually at the top of chapter 23, even though they're introduced at the end of chapter 22. That's more of just a useful purpose, because chapter 23 will be talking about how to find the electric field due to many charges, not just point charges. So just know the equations to find are at the top of chapter 23. All right, so let's talk about this point charge, this point charge creating this electric field. Using the definition that we have on the left, we know the force on a test charge or probe charge would be from Coulomb's law. So our electric constant, the charge on a test charge, the capital Q from this one creating the electric field, R in the denominator being the distance out to wherever the probe charge would be, and R hat meaning a radial direction. The force was either attractive or repulsive. In this case, it points away. It's repulsive. Well, the electric field is going to be the force this test charge feels, but taking the test charge out of the picture. And so the charge of the test charge disappears, and we're left with just the capital Q, the one creating the field, our same constant, which we can also write 1 over 4 pi epsilon naught, and then R. So ultimately, coming back to the picture, I'm taking away the point charge and just saying, hey, this location in space right here, this dot has an electric field that points away from it, the R hat. The strength of this electric field depends upon the charge that's creating it. It depends upon how far away from the charge I'm measuring this electric field. So this is our equation to calculate the electric field due to a single point charge. Depends upon what the charge is. It depends upon how far away from the charge we care to find it. Next chapter, we're going to have a bunch of different equations because we're going to talk about a number of different situations, like a charged ring, a charged disc, a charged plate, a bunch of different situations. But this is where we will start and build to get to those other equations as well. So electric field of a point charge created, so meaning the electric field created by this point charge at any region of space. Now, one other thing I'm remembering in a picture, to distinguish between a Q creating its electric field versus, say, a 2Q. Well, if we think about the equation up here, the electric field is going to change if this charge creating it changes. If I have twice the charge, then this electric field is going to be 2 times bigger. To represent that in a comparison, I shouldn't have drawn so many lines on Q. It's all good. So these are the lines for Q that I already drew, but pictorially, I would need to draw twice as many lines to represent there's twice the charge, which hopefully makes sense. If you remember, the closer the lines are, here, those lines are even closer, and they're going to mean that the field is even bigger around 2Q versus Q. So as you look at pictures, you'll have some questions that are asking you about electric field based off of just a drawing of the electric field lines. So they'll be even closer together when we have more charge, so more lines to do that. Field lines will point away from positive towards negative. If we ever draw a situation for electric field for a system of charges, these lines will never cross each other. They are always smoothly flowing. So I'll go through some conceptual questions and a couple problems with this, and then move into the next chapter.